what kind of networks qualify for high density Wi-Fi deployments? Can you give us an estimate in terms of the number of access point or the number of clients that are connecting to the network?
So I define high density not by the AP count, but by the contention pressure. So you are in high density when the airtime becomes the bottleneck. Some of the real-time examples are 100 students in the lecture hall, or maybe 30,000 fans in a stadium, or the conference centers where everyone at least have one or two devices with them.
Why does airtime become a critical resource in such deployments when compared to other metrics like throughput?
So in Wi-Fi, you see airtime is a finite resource, and then the file rate is just an option, right? Only one device can actively transmit at a time within the collision domain, right? So what matters most is how long your transmissions are going to happen, how much is your retry percentage, and how much of airtime is actual payload versus your overhead, right?
You also touched upon some of the best strategies for deployments in high density networks. So, if you have more details into that, can you please share?
You can make your cell size smaller, can remove your basic rate instead of making your broadcast multicast traffic goes at 6 Mbps, you can make it to go at 24 or maybe 48 Mbps. So there are a lot of techniques available, enable band steering or enable proxy ARP within the access points. What might surprise you is your percentage of airtime has been consumed by your overheads. So when I say overheads, what it actually means is it is a beacon or a probe request response or the ARC packet which is going around MDNS traffic, or SSTP is a simple service discovery protocol where like it enables auto discovery and configuration of your network devices, your retransmissions, your control frames, right? Be it RTS, CTS frames being seen over the air. And you would see a lot of these over there, right?
Hey everyone, welcome back to Weekly Wi-Fi Wisdom podcast series where we talk everything about Wi-Fi and the tech that surrounds it. I'm your host Sainath. I'm WLAN engineer at Candela Technologies, and in today's session we are joined by Asvin Kumar. She is currently working as senior TME and also as solutions architect at Arista Networks. I'm glad that he joined with us today. And in today's episode, we are going to discuss about high density Wi-Fi deployments and airtime distribution. Thank you so much for joining, Ashwin.
Thank you.
And I'm very much looking forward to hearing from you and learn about the topic. But before we dive in, please share a little bit about yourself, and then we can get into the topic.
So thanks, Sainath, for having me. Hello, everyone. I'm Ashwin from Arista Networks. I'm part of Wi-Fi TME team. I play a role of solution architect within Arista. A big part of my job is designing and troubleshooting Wi-Fi networks where we have hundreds and thousands of active devices, uh, being transmitting and receiving at the same time. Today, I'll be talking about high density Wi-Fi, where it really means. We'll be brainstorming about this concept. Um, Hope the session would be exciting. Over to you, Saina.
Yes, thanks. Thank you for the introduction, Ashwin. So let's get into the topic, right? So we are going to talk about high density Wi-Fi deployments. So let us start by defining that. So what kind of networks qualify for high density Wi-Fi deployments? Can you give us an estimate in terms of the number of access point or the number of clients that are connecting to the network? Some examples of such
Sure.
networks.
So I define high density not by the AP count, but by the contention pressure. So you are in high density when the airtime becomes the bottleneck. That's when multiple devices compete to transmit. And then the key question becomes who gets to talk for how long, right? In a real-time environment, some of the real-time examples are maybe 100 students in the lecture hall, or maybe 30,000 fans in a stadium, or the conference centers where everyone at least have one or two devices with them, or you can take an example of airports where most devices are active simultaneously. These are some of the real world examples that qualifies high density. From the radio perspective, I pay very close attention to when you have 30 to 40 active clients um, per radio. So these are the place where we have to pay close attention to clearly watch out for retries, um, and anything beyond this 40 to 50 active clients, and that's where like you start seeing high retries, uh, and then your contention increases, and sometimes your latency uh, becomes unpredictable when you have this dense environment, right? So that's predominantly because Wi-Fi is half duplex by nature. Once you have dozens of devices compete in the same contention domain, the efficiency kind of drops non-linearly. So that's where we qualify this high density networks.
Right. So you mentioned about airtime. So why does airtime become a critical resource in such deployments when compared to other metrics like
Yeah.
throughput?
So in Wi-Fi, you see airtime is a finite resource, and then the file rate is just an option, right? Only one device can actively transmit at a time within the collusion domain, right? So what matters most is how long your transmissions are going to happen, how much is your retry percentage, and how much of airtime is actually the actual payload versus your overhead, right? So what is so surprising that everyone must know about this airtime fairness is it is the amount of overhead contribution, amount of actual useful traffic is seen over there or not. So when you actually take a sniffer and try to capture it in a dense environment, what might surprise you is uh, your percentage of airtime is being consumed by your overheads. So when I say overheads, what it actually means is it is a beacon or a probe request response or the R packet which is going around MDNS traffic or SSTP, which is SSTP is a simple service discovery protocol, where like it enables auto discovery and configuration of your network devices, your retransmissions, your control frames, right? Be it RTS, CTS frames being seen over the air, and you would see a lot of these over the air, right? Um, you might see your radio might be using 70% of utilization,
Right.
but then you still get a complaint from the user, right? Why? Because out of the 70%, the 40% might be your actual useful traffic, but remaining are all the overheads, right? That's where like even at the 70% load, you would start seeing a lot of issues, right? So the throughput numbers generally don't tell you this. Your the airtime breakdown basically tells you this, right? That's why it is very key in a very dense Wi-Fi environment. Efficiency matters more than the speed.
Right. Totally agree with that. Again, when in such high density environment, let's say when hundreds of clients are competing for airtime, so how does CSMA CA protocol struggle to keep up?
Yeah, the CSMA CA is designed for fairness, but not for scale, right? So with a very small number of clients, your random back off works beautifully, right? But moment you see your active clients increases, what typically happens is your channel starts to become very busy. Your devices starts backing off. Your pollution increases, and then retries consumes additional airtime, right? So when I say retries, every retry is a full retransmission. Again, there is no kind of compression or no shortcuts there, right? Your retry is a full transmission again, right? So in a dense deployment, you often see that high channel utilization, right? Uh, you might see a good signal strength, but your throughput may be disappointing at that point in time. And then the retries, and then the latency gives you a very unpredictable results, and then your jitter also kind of spikes. So one key analogy we can use is like, let's say you are in a big conference room where you have 200 people in the conference room, right? Think of a case where the 200 people are politely waiting for the channel access, politely waiting to transmit a single frame to transmit something, politely waiting to get access to them. So it's practically not. I mean, though it's theoretically fine, you get your chance to talk, but in the class, in a classroom of like 200 people, how would you get even a small time to basically transmit, right? So that was the it is technically fair, but practically inefficient, in my opinion.
Right. So you mentioned about few metrics like retrace. So what are few such metrics which engineers can monitor to identify that there are issues with airtime distribution in the network?
Okay, so the metrics is very important. So what that comes to my mind immediately when you ask that question is the retry percentage, right? Um, Moment you see a retry that crosses 15 to 20%, then the airtime is getting burnt inefficiently somewhere, right? You need to pay a closer attention to that. Second is the airtime breakdown. So today, um, we talked about a little bit about the airtime distribution, right? So majority of the traffic which is seen over the air is not the usual traffic. Majority what you see when you sniff the package over the air is you have data versus management traffic versus control traffic versus multicast traffic, right? So if multicast or management traffic dominates, then that is a wasted opportunity. So you need to pay attention to your retry percentage, your airtime. Again, I'm just mentioning retrace, but then your MCS data rate, how close you are with an access point, all that matters. And then another key point that we need to metrics that you should watch out is uh, per client airtime usage, right? So you need to watch out. So in a dense environment, what happens is one or two clients takes most of the airtime. That is a very dangerous, right? So you need to watch out for outliers rather than the average, right? Uh, and then another
Right.
thing which comes to my mind is the channel utilization with low throughput, right? So you need to watch out for this. So your modern day campus network basically gives
Mm.
you dashboards that shows you the channel utilization. But if you happen to see a poor utilization, then that is something that corresponds to the contention inefficiency. So that's what it comes to my mind. But again, low data rate transmissions are the killers, that metrics that you need to watch out for.
Right. So you mentioned that few clients who are occupying more airtime can be dangerous to a network, right? So how do they affect adversely on the other clients' impact? And what are the most common clients that you see who exhibit these kind of
Yeah.
behavior? Since probably these come mostly
Yes.
under legacy clients, right?
Yes, they
So
are
please go ahead.
mostly a legacy clients. Again, there is another misconception going on with respect to airtime fairness. Fairness basically corrects the fundamental inefficiency. Without airtime fairness, the Wi-Fi is just a frame fair, not the airtime fair, right? So it's it is definitely when you have a mix of modern clients and then the legacy clients. Some of these legacy clients, especially IoT clients who transmit at 6 Mbps, tend to hog the overall airtime, right? So there is a trade-off here when we talk about airtime fairness. Is it really required to
Right.
be enabled in your network by default? Or do you need to enable them in density? What is when we should enable this is a first question, right? So first let us peel this down a little bit more on when we should use it. For this, like, let me take a quick analogy, uh, where let's take you have three modern clients. They are all like 11B client or maybe 11AX client transmitting at the highest possible data rate. And then you have a single IoT client, right? IoT, which is like a 6 Mbps client. Now, what happens if you try to give equal fairness to all of them, right? That means you have four clients, 25% of the airtime will be allocated for each of these clients, right? Out of these 25% of the client, the faster client tend to transmit faster, but the lower client, the lower speed client takes more airtime for transmitting a very small amount of data, right? So this brings kind of a disproportionation. So that is a trade-off, right? So now what happens is slower clients tend to talk more, take more airtime, but faster clients have to wait for his transmissions to happen. So this kind of like kills the nuance of airtime, right? So do you really need an airtime is the question in a dense environment. But the airtime also introduces the another problem where some of these low clients, low speed clients, maybe in IoT, who tend to like cog be the outliers and take most of the airtime, right? So you are forced to enable airtime, but where you wanted to enable is a real, if you, in my opinion, um, you have to enable airtime when you are in a dense, so that you don't see those outliers where like slow clients like in getting more airtime. But if you don't have a density, right, you don't have to enable airtime by default, right? So it's more like you have a traffic light. You take this analogy of a traffic light, right? The traffic light in the contented in an area is required when you see more of contention, more of traffic piled up, right? When you don't, and then the traffic light basically like helps the device, helps cars or bikes to move around. At the same time, if you don't have much of traffic in that area and having the traffic light unnecessarily in an area where it kind of kills your overall idea, right? You don't need to have them, right? So that is what I feel.
Right.
Airtime corrects the fundamental inefficiency, but you need to be very, very clear on where you wanted to enable them. And in modern day, this airtime fairness is more moving towards a scheduler, policy-driven scheduler-based mechanism.
Right. So, from your experience, how common is it for a small number of such poorly performing clients in terms of 810 affect the experience of everyone? So, in in practical deployments, right? How commonly
Yeah,
do
it
you
is
see
very
this?
much common. If I do a basic Wireshark captures in a certain channels like 2.4, 5, or 6, what I commonly see is a single IoT device flooding MDNS traffic, right? That is very, very common these days. If you just simply see each of these MDNS or Apple TV or Apple devices try to announce themselves, right, you would see more of them, right? Second is misconfigured clients, right? Misconfigured clients tend to send probes very, very frequently, right?
Mhm.
And then there is a sticky client transmitting at a very low data rate, or some of the clients are like some having a old driver versions are there. They are very buggy by nature. So I see two or more of these clients consume disproportionate airtime. Always you would see them, right? So from the wireless dashboard perspective, your average basically hides these facts most of the time. So you need to start your sniffers, you need to pay close attention to the per client statistics and then determine who is clogging more and then when to enable some of these features, right? So in a very high dense environment, you need to watch out for your outliers more than your average. That will clearly spot out where what kind of devices is misbehaving and what kind of distribution it is happening, right? Yeah.
Yeah. So, clients can be problematic, as you said. So, if there are sticky clients, let's say who are on very low data rates but still sticking to the AP, can you do something as an AP, enforce some policy, or maybe even disconnect that client, such problematic clients from your network? So, how does AP address these kind of
Yes. So
issues?
most of these behaviors that we talked about earlier are all client driven. We don't have any clients on the client driven. We cannot correct that client side of properties, but we can strongly influence the design. So there are a lot of best practices available. I'll let from a sticky client perspective, we can enable certain features on our access point, and I'm pretty sure most of the vendors who deployed their network in the campus site would, or be it any other site, right? They would start having. You'll have to start tuning some knobs within the access points, right? Detection of there is a sticky client flags available that where the AP monitor what is the signal in which this client is associated. And then what is the maximum data rate, retry percentage is happening for that communication. So AP in this modern world very easily detect this kind of an anomaly, right? So for when I say anomaly, what it means is we want a client to be connected to an access point at a very close, at a good signal strength, and then we kind of monitor the transmit and receive and see how much of retry is happening, and then it's very easy for us to spot out if the client is closer to an access point or like maybe like are connected far away, right? So there are some crude mechanism available. So when we know that the client is connected to a far away access point and transmitting data very efficiently, very effectively, then we kind of like send a dot frame over the air and disconnect the client so that the client can like do the scanning and then connect to a nearby access point. So that is one way you can kill the sticky client behavior, but there are so many other nuances available as part of best practice deployment. You can make your cell size smaller, and then you can make your access point transmit lesser, tune your TX power of an access point with which should be very less,
Right.
and then a couple of data rate tuning you can do. You can remove your basic rate instead of making your broadcast or multicast traffic goes at 6 Mbps, you can make it to go at 24 or maybe 48 Mbps. And then some of the best practice again could be like, reduce the number of SSIDs over the air as part of best practice. Keep it. I do see in some of the deployments, people, there are some of the customers keep increasing, adding more SSIDs over there, right? So we can enable some of these SSIDs, which is actually in use UPSK or some of these modern PSKs available based on the NAC, right? So it's instead of keep adding more SSIDs, you can design your network with the personal PSKs so that the SSID will be same, but many devices maybe using. So
Right.
there are a lot of techniques available, enable band steering or enable proxy R within the access point. So I've just listed a couple of the best practices that we usually follow on field uh, to control this. There is not much of client side control available, but if we design our networks efficiently with some of these key knobs in place on the day one, you can make your Wi-Fi efficient with respect, especially in the dense environment.
Right. I think these are very valid and very great points. So I have seen a Wi-Fi 7 router myself. So it's one of the routers that is particularly designed for gaming. And on 2.4 gigahertz band, it is maintaining backward compatibility till dot B. So whenever there is a multicast traffic that is running, they are
Yeah.
going on 1 Mbps data rate, and that is causing very severe effect on other clients. I have observed this. So yeah, the basic rates at least instead of going on the lowest denomination, probably they should
Yes. Yes.
spike up.
So you'll have to yeah.
Yeah.
Yes,
I've
I
tried
was
to.
about to say that
Yeah,
yes,
please go ahead.
we are spiking up instead of making it at 1 Mbps, you'll have to make it the basic rate to a higher value. And then you can also do, when you talked about multicast, I just realized that in the modern networks, right, you don't have to send multicast. Multicast can go as multicast, right? You can again convert the multicast and make it go as unicast over there. So these are some of the knobs available. You need to,
Unicast.
when you're
Right.
deploying, you need to watch out for those kind of features as available, and then try to turn on those knobs.
Right. Absolutely. Yeah, and previously you touched upon the overhead traffic, like in Wi-Fi. Let's take management or control frames, or in multicast, let's say there are some discovery protocols, right? I mean discovery frames. So how much of these, how much of this kind of traffic, what kind of distribution are they actually occupying in real deployments?
Yeah,
Is it
it
too
is.
high, or
It is pretty much
where
very,
does it
very
stand?
high. If you happen to see the packet, like the Apple devices, like MDNS is one of the major things, right? You kind of start seeing these clients advertise themselves quite frequently. I see a lot of overheads, especially when we talk about these overheads, right? You would see a lot of retransmissions. You would see a lot of management overheads happening, and then you see some of these protocols like SSTP, MDNS, kind of like keep announcing themselves over the air, and then this kind of kills the useful traffic. Not much of user traffic, but then these overheads would be higher. I see like 30 to 40% of them are there in every other networks. So actual problem is some of these devices are known, right? So what you can do to mitigate them, right? Some of them would be an ARP traffic, by the way, right? So we need to watch out for
Right.
uh, features like ARP suppression. ARP suppression or enable MDNS gateway. Let me go one by one, right? So in the case of ARP suppression, what happens is the client
Right.
wants to know when you wanted to talk. There is an east-west traffic. When I say east-west, like one wireless client wants to talk to another wireless client, right? So when it wants to talk to each other, it needs to know the MAC address of that client, right? So these ARP is basically an ARP is it's a flooding to see what is the MAC address for a corresponding an IP address, right? So so every time when a client sends this ARP request, then the AP kind of broadcast it over there, right? So AP has to maintain some of these tables, the ARP tables within them. If it knows that the second client, which is part of the same network, then instead of flooding the ARP request over the air, can it answer on behalf of the other client? Like AP can say, no, I already know the MAC address of this client. I will just respond to that ARP request. By that way, you can minimize the flooding happens over there. So in terms of MDNS traffic, again, some of these devices want to find the printer. Some of them wants to stream it in the Apple TV in a real time basis in a campus where like the lecturer, the students are there. The lecturer wants to use its Apple phone to do streaming and all, right. So you will need to understand the use case and then enable the what I call enable the MDNS gateway so that knows that okay, so these are the broad publisher, these are the subscribers, and then they kind of link them to each other. That way, that the traffic is efficiently sent instead of flooding it across all the VLANs in the network. So some of these techniques you could still do.
Right. So you also touched upon some of the best strategies for deployments in high density networks. So if you have more details into that, can you
Yes.
please
So what are
share?
all the let's take a case, right? So we wanted to know if we wanted to design for the capacity. There are some of these features, right? Say let's say in a dense environment, you tend to put more access points, right? So when you put more access points on your deployment, the channel reuse is going to be a problem, right? Because when you do 6, 12, when you say like 36, 44, 48, these kind of deployments, like no two access points should be in the same channel, right? When they are in the same channel, that it becomes like the co-channel interference would be high, and you tend to see a lot of contention over it, right? So you tend to have more access points, but you reduce the power of the access point so that the cell size is smaller. At the same time, you get more channels, right? You take an example of 5 gigahertz, like we tend to deploy 5 gigahertz with 20 or 40 megahertz channelization, and then you have 6 gigahertz to deploy at 80 megahertz channelization or above, right? When you have 20 or 40 megahertz, then you get more channels to use, right? So you can have one AP in 36, and immediate neighbor of that AP can be in 44 or 149, and then The another AP behind it can be operating in a different channel, or if it is happening in the same channel, then some of the features like spatial reuse or some of them, it is a channel reuse is possible, right? So you can basically do that. So that is one metrics we quite commonly use. We make sure that we in a dense environment we keep the cell size smaller. Second is we tend to have the lower TX power. We don't want the APs to transmit at a very, very high power, because the transmission can spill across and then it may go and hit your reuse plan, right? So you tend to, like,
Right.
have the TX power, the lower TX power on the access point. And then a couple of metrics we already, the controls we talked about is the reduce minimal data rate, or try to have your SSID is count SSID count lesser, and then enable band steering so that the client, instead of connecting it to 2.4, it can go and connect to 5 and 6 gigahertz, right? And then again, have a proper roaming threshold for your network. And another thing that comes to in my mind is you can start deploying the access point not based on the edge, right? So it means like one AP, and then the second AP can have a overlapping of at -60 to -65, right? By that way, though your cell size is smaller, but when it roams from one AP to another AP, it can roam at a much better data rate, right? By that way, your roaming will be faster, and then the client can be more efficient in the dense environment.
Right. So you talked about retries, but how do modern controllers or APs give more information about wasted airtime?
So I define wasted airtime is it's a airtime that does not deliver a useful payload. So when you say it doesn't deliver the useful payload, then what it comes to your mind would be, when you do a sniff capture, you would see a lot of retransmissions first. Second, you would also see a low rate multicast. If multicast going at the lowest possible basic rate, then you'd see a lot of multicast consuming, you are contributing to the wasted airtime. And then you would also see excessive management overhead. All right, a lot of management overhead. Your data traffic would be just 10 or 20%, but management will be 30 or 40%, and then you'll also see control packets more in the network. And then you would also see a redundant traffic, discovery traffics, right? That would happen. So, and how do you quantify it, right? So you need to have a better quantifying method. So
Right.
what to look in an high density, and of course, in the modern day, be it a controller less or a controller based network, you have a lot of dashboards available. One thing to watch out for is compare your airtime utilization versus your throughput, right? So that would be one of the way that you could quantify.
Right.
Second is analyzing the airtime distribution. You just do a basic airtime, the Wireshark capture, and then try to dissect your open air capture, right, without adding any filters or so. When you see, you see a pattern of the frame distribution, right? So how much is your beacons consumed, how much is your multicast consumed, how
Right.
much is your protocols like MDNS or SSTP is consuming. So analyzing the key frame distribution really matters. And then monitor for your retry percentage. How much of retry percentage is doing anything. Pay closer attention to anything which is 15 to 20% of retry is going to be very. It's not going to be anything efficient. And then estimating your airtime based on your MCS, right? And then the frame size. So some of these things you can use it to quantify your the wasted airtime. Some of them can be easily shown on the dashboards. Some of them, you will have to take the Wireshark captures, open air captures, and try to dissect and make the meaningful sense of it.
Yes. And when we are talking about dense deployments in enterprise networks. With the advent of 6 gigahertz, right? I think now most of the client devices are also coming with the support of 6 gigahertz. So, how does this shift in client devices with the support of 6 gigahertz help relieve the airtime bottlenecks in 2.4 and
Yeah,
5
absolutely.
gigahertz?
Absolutely. It would relieve a lot of pressure on the 2.4 and 5. Nowadays, we have a lot of slow. If when I talk, if I wanted to talk about the percentage, I do see the adoption on 6 gigahertz is not much these days, but I would say like 30 to 35% of client today in the mix environment is 6 gigahertz, and more clients are moving to 6 gigahertz. It's really good for us because it just removes the pressure from 2.4 and 5, right? Because we have when you design, you enable band steering such that you kind of push the client to away from 2.4 and be it connect to 5. Now when the client is a modern client which can support 2.4, 5 and 6 instead of 5, these clients would move to 6, and then the number of clients on the 5 gigahertz would be like less compared to earlier 1 or 2 years back. So when the number of clients are lesser in 5 gigahertz, then the more and more devices can transmit in a faster rate. That kind of helps the overall thing. But the key point is how much of adoption we have for 6 gigahertz, given that we have a lot of other factors, right? Because when the moment you say 6 gigahertz, there is a regulatory come into the picture, and then another factor that comes to the 6 gigahertz is uh, your transmit power on the client would be lesser, right? So that then you come into the indoor
Exactly.
deployment versus outdoor, because the client would transfer 60p lesser than what APs can transmit. How do you make your 6 gigahertz so attractive so that this clients which is dual band capable or tri band capable can move to 6 gigahertz efficiently faster, right? So all those things you need to basically watch out for and then deploy.
Right. Um, a quick question which I'd like to ask, with the advent of Wi-Fi 7 MLO, is MLO changing game in terms of airtime distribution and all? Because client can connect in a multi-link, right, association, and frame transmissions can happen. So
Yeah,
does it
yeah,
really change
absolutely,
anything?
absolutely. It's one
I'm
of
sorry.
the
Right.
good question that you asked on the airtime fairness, right? So we talked about a lot on the airtime fairness, whether we need to enable it, do I need to make it as a default or not? So all these airtime fairness which we discussed is mainly we know that for the legacy clients, when it is like consuming more airtime, that's where in the dense environment we need to go and enable. But when we enable them, they are all on a per radio basis, right? So that means it is completely on a link basis. A client can be in 5 gigahertz and then it tries to check the airtime, right? If the same client's connected to 6 gigahertz or maybe in 2.4, it's all on a per radio basis, right? That means per 2.4 or per 5 gigahertz is where this airtime fairness was for all operating. Now with MLO, the device can simultaneously transmit in multiple bands. It can transmit at 5 gigahertz as well as it can transmit at 6 gigahertz, right? So now do how do you take it from the fairness perspective? So you have allocated some airtime based on the 5 gigahertz where you have mix of clients. Now you have a mix of Wi-Fi 7 clients and Wi-Fi 5 clients, right? That means how much of airtime you need to allocate. Do you need to allocate equal number of airtimes of Wi-Fi 5 client and then the equal number of airtime for Wi-Fi 7 clients? But the client in Wi-Fi 7 is going to be a multi-band client, right? Because it is going to. So then
But
do you need to allocate again an airtime on the 6 gigahertz? Then the combined airtime is going to be more, right? For an MLO. So the amount, the 25% allocation for legacy, and then the same 25% allocation for 5 gigahertz versus 6 gigahertz, you would allocate 50% for an MLO client, and then you would allocate only 25% for your non-MLO client, right? So Wi-Fi 7, in my opinion, changes the airtime fairness game completely. We have moved from wi- airtime fairness to a policy-driven scheduler. right? So the policy-driven scheduler these days are very modern, that you don't have to give an equal airtime, but the scheduler decides uh, based on, now you can apply airtime based on SSIDs or based on clients, or you can apply airtime based on your applications too, right? So it's more like it's more like moving towards policy based airtime compared to the traditional airtime fairness. So from an Wi-Fi 7 perspective, uh, the airtime fairness, it's all policy or the scheduler based fairness. It's where the everything is moving towards. Again, within the scheduler type of mechanism, we have to decide whether it has to be a fair scheduler or whether it has to be a rigid scheduler. That I think it's mainly based on the needs and wants of the customer, and then needs and wants of the design or the key requirements on the use case of your own design.
Right. So I think scheduler is doing a lot of magic there uh, in in the airtime distribution. Maybe if you want to elaborate on that, you can elaborate on that topic
Again, the
with
scheduler,
more
it's
praise.
something could be we might be entering into the proprietary of it, because everybody decides their own way of handling things, right? So I don't want to
Right.
dwell deeper into the scheduler functionality, but in a high level, you could decide. We have discussed about the legacy clients utilizing the fairness, the which is like, the scheduling mechanism earlier was like giving equal airtime to the client versus scheduler deciding who knows the little bit more details about your link capacity and and your client capacity and all, right. Based on that, it can basically um, schedule traffic, right. And more of recent clients, modern clients coming in, with more and more clients having MLO enabled, then that becomes easy for the scheduler to prioritize the traffic based on SSIDs or based on application priority. You can schedule more airtime for them, and then you can easily eliminate disproportionation happening because of kind of low speed client or the legacy client hogging the maximum client, right? So you can easily prevent slow speed clients occupying the medium, and then you can basically use some of these schedulers, be smart enough to allocate airtime based on your application, or based on your SSID, or based on your per client.
Right.
You can make your schedulers can prioritize your traffic accordingly.
Yeah. So I think we are done with most of the questions. So if you have any closing comments, or if you would like to address the audience on this topic,
Yeah, no,
please
sure.
do.
So if there is one takeaway out of all this, right, I would say high density Wi-Fi is not about speed. It is about efficiency under contention, right? So airtime is finite, and every transmission has a cost, and every read, right, compounds the cost, right? So you need to be watchful for all of these. For a network to perform lot much better, you need to make sure you have right techniques, right design in place, and make sure that you minimize the wasted airtime, and then distribute client intelligently, so that based on some of these areas where if you happen to see there is a lot of contentions there, then you kind of distribute client intelligently to other bands. And more and more over the period of time, when new protocol comes, the client would be even more smarter, because the scheduler is in right place to intelligently shift the clients to the bands which is cleaner, and then you tune your RF deliberately, and then monitoring that continuously. You'll have to monitor. So every design that you apply, it's not going to be the constant design. You'll have to keep reassessing your network, and that's where a lot of your AI and ML techniques comes these days, to constantly monitor your network and then apply the right knobs for your network, customized for your networks. Whatever metrics I just told on this podcast is just an high level metrics, but it may not be like, widely applied everywhere, right? Based on the needs and wants, you and these are the techniques that you can use it. Just wanted to, you should understand your airtime, then you would understand the dense Wi-Fi very clearly and precisely.
Great. Thank you so much, Ashwin, for doing this, for sharing all the wisdom with our audience. Uh, I I really hope they'll love this and gain insights for whoever are working with high density Wi-Fi deployments. So thank you, and that's all for today's episode. Keep watching Weekly Wi-Fi Wisdom, and we'll catch you guys in the next one. If you like the episode, please like, share, subscribe. And if you have any questions for us, Ashwin, please leave them in the comments below. I'll try to get those addressed by the
Sure.
next
Thanks,
episode.
Sainath, for having me here. It's a pleasure to be here in this podcast. Thank you. Thanks, everyone.